Good day, everyone. I am Joanne Christine S. Dakuyan. In this video, I will be discussing titanium dioxide nanoparticles. So before we get started, I have a question for you all. So have you heard a thing about titanium dioxide nanoparticles? If you haven't, along the discussion, you will discover and realize that you have been utilizing titanium dioxide nanoparticles in your everyday life and encountered a product that contains this kind of nanoparticle. So this presentation will cover the definition, the application in real-life situation, and importance to us of titanium dioxide nanoparticles. And at the end of this discussion, you will be able to discern, you will be acknowledged as to how titanium dioxide nanoparticles affect our lives in a variety of amazing ways. So let us get started. First, let us define what titanium dioxide nanoparticles are. So, titanium dioxide nanoparticles, also called ultrafine titanium dioxide or nanocrystalline titanium dioxide or microcrystalline titanium dioxide, are particles of titanium dioxide, obviously, but with diameters less than 100 nanometers. So TiO2 and Ps or titanium dioxide nanoparticles are non-toxic in nature, biocompatible, reusable, and chemically stable with efficient and antimicrobial properties. Of the three common TiO crystal forms, brochite, anatase, and rutile, TiO2 nanoparticles are produced in the rutile and anatase forms, and like larger TiO2 particles, TiO2 nanoparticles are transparent rather than white. In relation with this, ultraviolet absorption characteristics are dependent from the crystal size of titanium dioxide. So since titanium dioxide nanoparticles are ultrafine, meaning they are small, it has a strong absorption against both ultraviolet A, which ranges from 320 to 400 nanometers, and ultraviolet B that ranges from 280 to 320 nanometers radiation. So this is how a titanium dioxide nanoparticles look like. So these are, as you can see here at the second picture, the three common crystal forms of titanium dioxide are rutile, brochite, anatase. Each of them varies differently in their physical compositions. Titanium dioxide nanoparticles are photocatalysts, which means that they have the capability to use energy in light to catalyze reactions with other molecules at reduced temperatures. Although other photocatalytic materials are available, researchers have found that titanium provides the best performance in sunlight. So, this is one of the major characteristics of titanium dioxide itself. It provides the best performance in sunlight. Another property of titanium dioxide nanoparticles is that it reflects all colors visible in the light spectrum. Therefore, the light reflected from titanium dioxide nanoparticles is white. So this characteristic makes it useful as a white pigment in paints and may make for white residue in your skin when you slather on sunscreen. So since we are already done in defining and providing a short background for titanium dioxide nanoparticles, let us move on to its applications or uses. So first thing first is the sunscreens. Your sisters might be using this right now, your mother. So I think this is a very common product that contains titanium dioxide nanoparticles. So ultrafine TiO2 is used in sunscreen due to its ability to block ultraviolet radiation. while remaining transparent on the skin. So TiO2 particles used in sunscreens typically have sizes in the range 5 to 50 nanometers. Since I have mentioned earlier that titanium dioxide nanoparticles has a diameter less than 100 nanometers. Following this is titanium dioxide nanoparticle is also used in housing and construction as an additive to paints, plastics, cements, windows, tiles, and other products for its ultraviolet absorption and photocatalytic sterilizing properties, for example, in anti-fogging coatings and self-cleaning windows. Engineered titanium dioxide nanoparticles are also used in light-emitting diodes and solar cells. So if you have solar panels in your home or this kind of light-emitting diodes, please be aware that it contains titanium dioxide nanoparticles. So, forming titanium dioxide nanoparticles allow researchers to form photocatalysts that are more effective because they have more surface area available to react with other molecules. Also, in the particle form, titanium dioxide can also be used in creams and coatings that absorb UV rays or ultraviolet rays. Some companies use titanium dioxide nanoparticles as part of a film that uses the energy and light to start a chemical reaction that kills the bacteria on surfaces. In addition to this, researchers are also developing methods to use the photocatalytic properties of titanium dioxide nanoparticles to destroy cancer tumors. They are delivering titanium dioxide nanoparticles to cancer tumors using targeted drug delivery methods, then shining light on the tumor. The TiO2 nanoparticles use the energy from the light to add an electron to oxygen molecules which proceed to destroy cancer cells. Isn't it amazing, right? So titanium dioxide nanoparticles can also be applied in environmental improvement, wherein it helps remove pollutants from the atmosphere such as NO2 released by exhaust gas and other sources. In addition, SOx, a harmful inorganic substance in the atmosphere, can be broken down with the help of TO2 nanoparticles. Titanium dioxide nanoparticles is also present in pharmaceutical applications, wherein its photocatalyst often involves sterilization and virus restraint due to its ability to damage cell membranes, solidify virus proteins, control virus activation, and capture infectious particles. It has been shown to eliminate 99.97% of microorganisms. Coliform, green suppuration bacillus, golden grape coccus, mildew, suppuration fungus, and other bacteria are examples of targets that TiO2 nanoparticles can kill. For example, studies have demonstrated the sterilizing ability of titanium dioxide using coliform and golden grape coccus. A population of 3,105 coliforms and 3,2105 golden grape coccus were reduced to 10 after 24 hours of reaction, which had proved that TiO2 nanoparticles can indeed kill bacteria. Titanium dioxide nanoparticles are also ideal for wastewater treatment. Why? It's because of their low cost, corrosion resistance, and overall stability. They can be used as solid phase extraction or SPE packing material to preconcentrate and extract heavy metals from water for surface water remediation. Diazinon is an organophosphate insecticide that is found in groundwater and is classed as a relatively harmful toxin by the World Health Organization. When ultraviolet light and titanium dioxide nanoparticles doped with iron, it showed 98.58% diazinon removal efficacy. And of course, titanium dioxide nanoparticles won't be absent in agricultural fields. So TiO2 nanoparticles have been shown to boost the rate of photosynthesis in spinach crops. In other species, more pigmentation was detected in ZMAs sprayed with nano TiO2 during the reproductive stages of the plant, leading to increased crop production. When applied to tomato plants as an aerosol, TiO2 nanoparticles were found to be more effective at increasing photosynthesis and lycopene content than TiO2 nanoparticles used as a soil amendment. Now that I have fully explained the applications of titanium dioxide nanoparticles in environment, wastewater, and agricultural industry, I'll move now to the applications of TiO2 nanoparticles in the medical industry. The first issue in medical industry where titanium dioxide nanoparticles is included is the drug delivery systems for cancer therapy. So as I've mentioned earlier, titanium dioxide nanoparticles are now being examined to be utilized in treating cancers. So traditional chemotherapy cancer treatment can have catastrophic effects on cells due to their toxic nature. As a result, the focus has been placed on how nanotechnology can be used to diagnose and treat cancer. Currently, the most significant challenge to overcome is reducing the side effects of nanotechnology-enabled drug systems. And lastly is the usage of titanium dioxide nanoparticles in long-lasting medical implants. So TiO2 nanostructures have been successfully used in essential medical products such as implants to address some of the topological issues around titanium implants. Deployment has been demonstrated in bone implants, dental implants, and other applications.